Hello guys, so this is a problem from International Mathematics Olympiad 1995 and it says to prove this sum is greater than 3 over 2. Try it out and see if you can get to the solution. So it says ABC are positive real number and ABC is equal to 1. Okay, this is our first hint. So when I look at this equation, I see a cube in the denominator, and that's what we don't like. We don't like big powers in denominator. We have to change this somehow, because this is gonna be big problem if we carried this a cube in the denominator. So the only thing that I could think of right now for changing this is if I let 1 over a is x, then 1 over a cube would be x cube. Okay, so this would somehow like remove this a cube from denominator. So this is my first strategy and the very first thing that comes to my mind when I look at this question. Denominators have to be linear and as simple as possible. Almost always. Okay, so let x is equal to 1 over a, and you let y is equal to 1 over b, and you let z is equal to 1 over c. Okay, we have been given ABC is equal to 1. From here we can also deduce that x, y, z would be 1 over ABC, which implies that x, y, z would be 1 as well. Okay, so we have got these two things, and now let's apply this into our first term, this term. Let's see what do we get. So 1 over a cube b plus c. If I substitute x, y, z in place of this, we will get 1 over y plus 1 over z, right? This would give me x cube over y z plus y plus z. This would give me x cube into y z over y plus z. Okay, now I have got this very new thing in denominator, but we know that x, y, z is equal to 1. From here we can say y, z would be 1 over x. Okay, so 1 over x would cancel out with x cube, and you are left with x square over y plus z. Okay, this seems pretty clear. For the first term we got this. Similarly for the second term we will get. Similarly, if you apply this whole thing on the second term, you will get, I hope, y square plus z plus x. Yeah, and for the second term, and for the third term, for this term you will get z square over y plus x, right? So just sum these all up. X square over y plus z plus z square plus plus y square x plus z plus z square x plus y. Okay, so let's call it as so if I apply Cauchy-Schwarz, no, I'm applying T2's lemma. If I apply T2's lemma on S, do you know what T2's lemma is? T2's lemma says that like the powers in the numerator would become x plus y plus z whole square, and the sum of all the numerators like 2x plus y plus z, because if you sum these all up, if you sum this all up in the numerator, it will become 2x plus yz would always be less than this whole s. Okay, this thing will be greater than this thing. This is what T2's lemma says. So in the numerator you will just use you will convert sum of squares into sum, and then from there you could deduce this. So by T2's lemma you get this, and then you get this x plus y plus z cancels out with the upper, and then you get x plus y plus z over 2. Now I don't have anything to do with this thing, but how, like x plus y z, I have to prove that this sum is greater than 3 over 2. So but I have this x plus y z over here, I have to somehow remove this. So we know that x, y, z are positive real numbers, right? Positive real numbers. So I can apply AMGM on this, apply AMGM inequality. If I apply AMGM inequality on this, we will get 3 cube, and then you will get something like x, y, z. Since x, y, z is equal to 1, we will get x plus y plus z is greater than 3, okay? So if you plug in that minimum value, this is the minimum value of it in this sum, you will get 3 over 2. So any larger value, so this is the even with minimum value s is greater than 3 over 2. Any larger value will definitely result in s to be greater than 3 over 2. For example, if you place this is the least value. If it can take 5, x plus y z plus can take 5, it takes 5, the sum is still greater than 3 over 2. If it takes 2, the sum is still greater than 3 over 2. So even with the minimum value, the sum is greater than 3 over 2. So any larger value will result in sum to be greater than 3 over 2. This proves this whole question, okay? Hope it helps.